Good morning. Welcome to this Conservation Applied Research and Development, or CARD webinar today on air-to-water heat pumps, a cold climate solution for high-efficiency cooling, space heating, and water heating. Thanks so much for joining us today. I'd like to cover a few housekeeping items before we start. All attendees will be in listen-only mode. We will answer all questions at the end of the presentation, but as questions do occur to you, please type them into the Q&A box and send them to all panelists. The Q&A box can be opened by clicking the ellipsis in the lower right of your screen as indicated on this slide. We will do our best to answer all questions within the time allocated, but if we don't get to some, we will answer them after the webinar. This webinar is being recorded and will be available on the department's website in approximately a month. All registrants of this webinar will be emailed the PowerPoint slides within a couple of weeks of this webinar broadcast. And finally, if you'd like any closed captionings on this webinar, click the CC bubble in the lower left of your screen. I am Lindsay Anderson, the Utility Energy Conservation Research Planner at the Minnesota Department of Commerce in the Division of Energy Resources within the Energy Conservation and Optimization, or ECO, business unit. In that role, I identify and analyze gaps within utility energy conservation and optimization programs and coordinate and plan research to fill those gaps. The CARD program is a major tool of that work. With me today is Lauren Sweeney, a principal energy planner, also within the Energy Conservation and Optimization business unit at the Department of Commerce. Lauren specializes in the regulation of electric and gas utility energy efficiency, load management programs, as well as the staff lead on the technical reference manual. She is the department's project manager of the research that is the subject of today's webinar. Our presenters today are Samantha Hill, Josh Quinnell, and Ronal Tadawe from Center for Energy and Environment. Samantha Hill is a research engineer at Center for Energy and Environment, where she evaluates and studies innovative technologies to improve residential and commercial building energy efficiencies. Ronal Tadawe is a research engineer at Center for Energy and Environment, where he studies emerging technologies in building energy efficiency and electrification. His recent work includes the development of several modeling tools and calculators for end-use electrification measures and an investigation of special utility rates for air source heat pumps. Josh Quinnell is a senior research scientist at Center for Energy and Environment with 13 years research experience in building science. Josh is currently working on heat pumps, building envelopes, and the impacts of electrification on the grid. Welcome, Samantha, Ronal, and Josh. We look forward to your presentation today. This webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of this fund is to help Minnesota utilities achieve their energy savings goal. $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects provide utilities with data to enhance energy efficiency program designs within their energy conservation and optimization portfolios. As you can see by the pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is within the residential sector, and the presenters will discuss results from a recent CARD project that characterized available air-to-water heat pump systems, determined the best air-to-water heat pump system configurations to serve Minnesota residential load priorities, and tested those configurations within field installations in representative applications to measure the energy savings and cost effectiveness for heating, cooling, and hot water loads. Now with that, I'll turn it over to Ronal for today's presentation.
All right, thank you very much. Good morning, everyone, and thank you for joining us to learn about air-to-water heat pumps, an exciting new product class that could be a cold climate solution for high-efficiency cooling, space heating, and water heating. My name is Ronal Tadawe, and I'm joined today by Samantha Hill and Josh Quinnell. I will be delivering today's presentation, and Sam and Josh are in attendance to field questions at the end of the session. Next slide. So let's have a quick look at our agenda for the morning. And as this is a newer class of heat pump, we'll start by looking at what defines the technology and how it is different to more familiar heat pump options. Then we will look at the types of air-to-water heat pumps available at the moment and their key differences. From that, we'll progress on to introducing our field evaluation of these systems with a quick background before looking at results for performance, energy savings, and economics. Then we'll close it out by looking at conclusions, barriers, and opportunities before opening up for questions. So without further delay, let's jump right in. Next slide. So first off, what is an air-to-water heat pump? Next slide. Well, unlike with many of the questions we tend to ask in heat pump land, the answer is actually really simple. Air-to-water heat pumps are air source heat pumps with hydronic distribution, in the same way that air-to-air heat pumps are air source heat pumps with air distribution. And that's it, that's my entire slide. Fundamentally, air-to-water heat pumps still extract heat from the ambient air outside the home and move that heat into the home. The only difference is that air-to-air ASHPs use forced air distribution, while air-to-water heat pumps use, you guessed it, water-based distribution. And they distribute that heat via low-temperature radiant systems like in-floor slabs and fan coils, and also through forced air ducted distribution systems and even domestic hot water supply in some cases. So let's have a look at what this looks like as a simple schematic on the next slide. So here we have a typical air-to-air ASHP at its core. The refrigerant loop here is shown in yellow. It has an outdoor unit with a refrigerant-to-air heat exchanger, expansion device, and compressor. Indoors, the cycle is completed by another refrigerant-to-air heat exchanger that releases the heat into air distribution systems like ductwork when in heating mode. Now let's take a mental snapshot of this diagram before we look at how much of this changes with an air-to-water system on the next slide. So this is a typical air-to-water heat pump system, which you'll remember is still an air source heat pump. Immediately, you'll notice that the refrigerant loop on the left looks almost identical to what we saw before. The only difference here is that instead of releasing heat to air distribution systems, the refrigerant transfers that heat to a water loop that then interfaces with hydronic distribution systems like in-floor radiant heating. The refrigerant to water heat exchanger can be either indoors or outdoors, as we'll see when we look at the types of systems on the market in the next section of this presentation. Next slide. But first, let's touch on the pros and cons of using hydronic distribution. There are many reasons you might want to pair an air source heat pump with a hydronic distribution loop. For one, the heat capacity of water is way higher than air. It can hold more than 3,500 times as much energy as the same volume of air, and that means you don't have to spend so much energy moving it around for the same heat output. Modern hydronic emitters are also compatible with lower supply temperatures, and that includes radiant flooring. Reducing supply temperature requirements can in turn improve the efficiency of the heat pump cycle. In addition to this, air-to-water heat pumps can provide a ton of flexibility as well, with diverse emitter configurations, zone control, and even potential for integration with domestic hot water and with thermal energy storage. Potential disadvantages to this include the addition of a refrigerant-to-water heat exchanger, like we saw in our schematics, that would introduce a new source of potential inefficiency. And one that's pretty relevant to our climate is the need for sufficient protection against the hydronic lines freezing and bursting. This is not new to hydronic systems, but it is not a consideration with traditional air source heat pumps that just use refrigerant and air. The addition of antifreeze like glycol will reduce the heat transfer efficiency of the hydronic fluid, and the sites we monitored included the addition of between 25 and 50% glycol to the water loop. This is of particular concern with in-floor radiant heating, where, as you might imagine, contractors and homeowners are rightfully cautious to avoid freezing and bursting within the slab. This isn't always needed, however, as systems without hydronic lines outside the envelope or in unconditioned space wouldn't have a risk of freezing, but contractors and homeowners may still elect to add antifreeze for peace of mind, as was the case in our installs. And finally, hydronic distribution may pose some site-specific challenges in retrofit scenarios as well. This includes retrofitting homes with higher temperature distribution systems like high-mass cast iron radiators that are designed for supply temperatures that are much higher than can be achieved with a heat pump. And with that, let's turn the page to our next section, where we'll look at the types of air-to-water heat pumps on the market. Next slide. Despite being a relatively new type of product in our market, there are already dozens of models and configurations that are available at the moment, including the manufacturers that you see here on the right. And more have continued to reach the market since we did our market scanning effort at the beginning of this project in 2021. Part of this is due to how well established air-to-water heat pumps are as a product category in Europe and in Asia. Many products now available in this market are associated with European manufacturers and products designed for international markets. Just like other ASHPs, air-to-water heat pumps function mainly as space heating systems, although many also provide cooling and some can even provide domestic hot water heating, including one that we installed in our field study, but we'll talk more about that later. Next slide. Here are some examples of air-to-water heat pump products from Arctic, SpacePak, and Electro Industries. There are two main air-to-water heat pump configurations, which we will call either monoblock or split systems. In a monoblock system, the refrigerant-to-water heat exchanger is inside the outdoor unit, or ODU, and what you get is all the important bits packaged in a single, kind of large box outside the home, and hydronic fluid is what crosses the envelope. In a split configuration, the refrigerant-to-hydronic heat exchanger is inside the home, and refrigerant crosses the building envelope. The indoor heat exchanger is packaged with other system components in what we call the indoor unit, or IDU, which is the smaller box in that middle picture. The split-type air-to-water heat pump system has an additional subcategory that we call third-party split. This is an AWHP system that is sold as an IDU-only solution, much like a traditional electric boiler, but that is designed to interface with a traditional third-party air source heat pump as the outdoor unit. So that image on the right just shows the IDU, and you would pair that with your favorite non-communicating outdoor unit. In our market scanning effort, we shortlisted 47 systems that were potential candidates for field installations, 34 of which were monoblocks, which is the dominant configuration in the European market as well. A further 8 products were third-party split systems, and 5 were matched split units like the SpacePak system we see here. Additionally, 44 of the 47 were able to provide cooling in addition to heating, and 35 products explicitly note hot water integration as well. All right, that was a lot of words all at once. So let's look at another schematic on this next slide that should clarify the differences between these system types. This is a schematic of a monoblock, split, and third-party split system. And there's a lot going on here, so let's start at the outdoor unit for each of these and then move downwards. So starting at the monoblock ODU on the top left, we see that the hydronic loop in blue is what crosses the building envelope with the dashed line, going downwards from the outdoors to the indoors. Once indoors, there is no additional heat exchanger, but there may be an optional indoor unit that packages controls and other system components together for ease of install. There is then an inline auxiliary electric boiler that serves as a backup heating system that can supplement the heating provided by the heat pump if needed. This is then connected to whatever emitters are present in the home, be it a radiated floor, low temperature radiators, fan coils, or a hydronic coil for forced air heating. This is also where domestic hot water comes into play, as the system may supply preheating to a DHW tank as an additional output to the IDU. So now let's look at the proprietary split system. This is essentially identical except for 2 key points. The refrigerant line is what crosses the envelope this time, as you can see in yellow. And there is certainly an indoor unit containing the refrigerant to hydronic heat exchanger. In a proprietary system, the IDU and ODU are a package deal and are sold together in a sort of match system like the SpacePak unit in our last slide. In what we call a third-party split system, the ODU can be any compatible air source heat pump outdoor unit, which works fine for this type of system because the refrigerant to hydronic heat exchanger is in the IDU and is therefore external to the outdoor unit. The benefit of a monoblock is that the ODU is pre-charged with refrigerant and therefore does not require refrigerant work at time of installation, whereas the split system will be charged with refrigerant on site. We should also note that even though monoblocks are the only system with hydronic fluid traveling outside the envelope, the split systems may still include some glycol added to the hydronic lines if there is a risk of freezing in unconditioned space. Next slide. So now we know a bit about how these systems work. Let's look at how we evaluated them in our field study. Next slide. Air-to-water heat pumps are relatively new to Minnesota. ASHPs are getting less new each and every day, but they still represent a small but growing fraction of the residential HVAC market in our state. and we are still dominated by natural gas as the most common heating fuel. So air-to-water heat pumps are just the newest iteration of an already relatively new technology. And so, as you might expect, they currently have almost no market share in Minnesota. That's not to say there isn't a home for them. We certainly have a significant number of hydronically heated homes in our state that could benefit from a high-efficiency option. And they form sort of two camps on average, where we have a lot of single-family homes built in the early 20th century with panel radiators, and we also have a notable contingent of single-family homes built since 2000 with in-floor radiant heat. And that's just focusing on single-family, not multifamily applications. Next slide. So to keep things simple, single-family homes were the focus of our field study. Our goal was to characterize air-to-water heat pump systems applicable to single-family homes in Minnesota and suitable for our climate. To do this, we field monitored 4 air-to-water heat pump systems retrofit into 4 single-family homes to measure their performance. And you can see roughly where these 4 sites were on the map on the left. 3 of the 4 participating homes lie at the boundary of IECC climate zones 6 and 7, and the southernmost site is in zone 6. Our project oversaw air-to-water heat pump retrofits, which occurred from late 2021 to early 22, and we monitored these sites through this summer in 2023. Next slide. This field project installed 2 third-party split air-to-water heat pumps and 2 monoblock systems. The split systems were paired simply with radiant floor heating, with no cooling or domestic hot water capability. The monoblocks were paired with radiant floor heating and a central hydronic coil on pre-existing air handlers that allows them to provide heating and cooling. One monoblock site was also configured to support domestic hot water by heating a domestic hot water preheating tank. All installations replaced existing electric boilers and essentially kept a balance of system components in place. The primary emitter for all homes was the radiant floor, which is compatible with AWHP supply temperatures. And we had concerns about retrofitting high temperature panel radiators that could be undersized for the lower supply temperatures that come with a heat pump retrofit. Next slide. So here is a table for details on these sites and systems. Site 1 was in Foley, Site 2 in Garfield, Site 3 in Faribault, and Site 4 was quite close to Site 2, also in Garfield. The 2 split systems were NorAir third-party split units paired with a 5-ton Bosch Bova non-communicating air source heat pump outdoor unit. Site 1 had in-floor heating as its primary emitter, as did Site 2. Both sites had an auxiliary electric resistance boiler included as part of the IDU package from Electro Industries. Site 1 also had a wood stove in the main living area, and likewise Site 2 had a propane fireplace. The 2 monoblock systems are Enertech Advantage 5-ton units that come with an accompanying IDU that integrates controls and auxiliary heat into a single box. Both sites added forced air heating and cooling via hydronic coil above the furnace and air handler combination, but only Site 3 was hooked up to a Turbomax indirect domestic hot water preheating tank. This site also retained their existing water heater as a backup for when the air-to-water heat pump is prioritizing heating and cooling. Site 3 had in-floor heat supplying the lower level, while the upper level was solely heated by a central furnace and air handler that interfaces with the heat pump via a hydronic coil. They also retained their old propane furnace for backup. Site 4 was very similar to Site 3, although this home also had 2 propane fireplaces. So now let's look at some pictures on the next slide. Here is what a split system looks like. Both of these images are from Site 2 in Garfield. The ODU is literally a commercially available air source heat pump compressor unit. In this case, it's a Bosch Bova outdoor unit as shown in the right picture. And if you weren't sure about air-to-water heat pumps just being ASHPs, I hope this puts you at ease a bit. Because if I only showed you the image on the right with no context, you probably wouldn't be able to tell whether this is an air-to-air system or an air-to-water system. The IDU on the left is the NorAir unit that simplifies connections to that of a boiler and is also produced by a well-known boiler manufacturer in Minnesota, Electro Industries. You can also see some of the existing connections to the home's in-floor hydronic system here, with the hydronic manifold mounted just below the IDU in the left image, with tubing going straight into the slab from there. Next slide. And here's the Enertech monoblock system as installed at Site 3 in Faribault. While not a defining feature of a monoblock system, this Enertech unit did have an IDU which included some additional components like a hydronic pump and an expansion tank, as well as system controls. It's a bit hard to see in that picture, but the IDU is the glowing rectangle on the left side of the image. In this image, it's been opened up so we get a good look at its insides, graciously illuminated by that little work lamp. Beside the IDU, you can see more hydronic manifolds, some going straight into the slab for nearby loops, and others traveling upwards to get to their heated garage. The tank on the far left is their existing tank water heater, and on the right is the new Turbomax domestic hot water indirect preheating tank. The image is taken standing in front of the furnace and hydronic coil, and you can see some of the ductwork at the top of the photo. One thing to notice about monoblocks is that their ODUs can be pretty big in comparison to other heat pump systems, just because they contain more components like the refrigerant to hydronic heat exchanger. That may be a factor to consider when you're siting the ODU outside the home as well. So there's a picture of me on the right standing beside the ODU, and for reference, I like to think I'm about 6 feet tall on a good day, so that unit is about the size of a comfy Manhattan studio. Next slide. So now let's get to the meat and potatoes, which are our performance results. Next slide. Displayed here is daily data for average heat delivered in BTU per hour on the y-axis, plotted versus outside air temperature on the x-axis for sites 1 and 2. Here, the black data is output delivered from the heat pump, and the red is from the boiler. We'll see the same data wrapped up in a cleaner diagram on the next slide, but what I want to call out here is the boiler data from year 1 versus year 2. We found that, out of the box, controls were not necessarily optimized to reduce boiler usage in mild temperatures, and this is most evident at Site 2, where we've marked data using the default control settings with hollow red circles from the aux boiler. And the filled circles there show data from after we modified the control settings to better prioritize the heat pump. And as you can see, that drastically reduced the boiler usage above 0 Fahrenheit. Next slide. Here is the same data from the second winter only, binned by OAT and including only data from after the controls adjustments. We found that these systems perform very similarly to their air-to-air cousins with an auxiliary backup heat source. The key point here is that they are able to displace a majority of the home's heating load through the year. Moving from right to left on each plot, we can see more clearly that the boiler begins to seamlessly make up for the shortcomings of the air-to-water heat pump as it starts to lose capacity in cold winter. Another point to note is that the Bosch compressors at these sites are rated to -4 degrees, which is why you'll start to see a drop-off at that point. Next slide. This is the same plot this time for the two monoblock systems. The heat pump is in navy, the boiler is still in red, and this time we also have the propane forced air heat delivered in teal. And again, we see that the bin data is on the next slide, but we're looking at the hollow teal circles versus the filled teal circles for now. Site 4 had an extended period of time for which the upstairs thermostat control in the propane system was placed in emergency heat mode, meaning that this thermostat never called for the air-to-water heat pump while the manufacturer worked to troubleshoot system issues at the site. Unfortunately, about half the monitored heating season was affected by this. Next slide. So now let's look at the bin data again, this time only for days where the heat pump was fully operational and the thermostat was not in emergency heating mode. We see another smooth transition in colder weather, where the boiler and propane integrate themselves seamlessly to make up for the capacity limitations of the heat pump. At Site 4, this doesn't occur until a very low temperature of about -5 Fahrenheit. But note that much of the data from the previous slide has been filtered away as those points were affected by the emergency heat setting. Unlike the split systems, these heat pumps did not have a minimum temperature of -4, and so we can see that they operated well below 0. Next slide. So next, let's look at the achieved system COPs, averaged by day and displayed versus daily average ambient temperature on the x-axis. The plot on the left is the daily data, which is then further averaged into two clean profiles, one for the monoblock and one for the split system, displayed on the right. On average, the system COPs are a significant improvement over electric resistance or propane heating alone, which always have COPs of less than 1. Site 3 had the best average daily system performance as the only site that did not have major controls modification related to auxiliary heat used during the study. Excuse me. Comparatively, Site 4's average COP between 10 Fahrenheit and 50 Fahrenheit was substantially reduced by regular propane usage, which has been filtered out for this diagram. This is also the reason why there are so few red dots on the left side. The third-party split systems at sites 1 and 2 proved less efficient than either monoblock system below about 30 Fahrenheit, but their average performance exceeded that of the monoblock at site 4 above 30 Fahrenheit. As expected, daily COPs across the board were best in the warmest weather. The reason they dropped so sharply above this point is simply because there was very little heating load at those temperatures, resulting in very low daily COPs due to the effects of standby energy. Below zero, all system COPs fell toward that of the aux heat sources, as the heat pumps were used less and less. The monoblock systems were able to maintain COPs above 1 to slightly colder temperatures than the third-party split, which had a higher ODU lockout temperature of -4 degrees Fahrenheit. The seasonal COP for the split system was 1.35 and was between 1.7 and 2 for the monoblock. Next slide. So now one thing we haven't talked about yet is cooling. Here we have two charts, one for each of the monoblock sites, which are the only sites with cooling. Both charts show cooling performance curves with daily cooling COP on the y-axis and OAT on the x-axis. Note that these COPs do not include latent loads and so are based on sensible cooling only. Site 3 has quite a few days with 0 or nearly 0 COP. These data points are typically days where there is both heating and cooling, which cancel out in our math to produce very small daily cooling COPs. There are also some days here where there was very little cooling delivered, even if there was no heating that day. Site 3's data are split into hollow points for when domestic hot water was enabled and filled points with no DHW capability on those days. A big takeaway from here is that the system having to switch between cooling mode and heating for DHW preheating has a clear cooling energy penalty, at least at the daily level. On average, the calculated COP at Site 3 above 70 degrees is 1.54 with no domestic hot water, or 1.35 with DHW enabled. Note that the configuration of these systems does not allow the unit to dump heat from cooling mode into the domestic hot water system. That might be one way to improve efficiency, but it would require significant system modifications. Site 4 didn't have these penalties, but we still have two distinct efficiency regimes in this chart, with filled circles from summer 1 and hollow circles from summer 2. The average cooling COP from summer 1 was 2.61 compared to 1.79 in summer 2. This was tied to multiple adjustments being made by the manufacturer and installer, ranging from tweaking target supply temps to combining in-floor loops and even removing the external hydronic separator. These adjustments were primarily driven by heating performance, but they had an adverse effect on cooling season as a result. Air-to-water heat pumps may increase cooling efficiency if they can operate to their potential, but such issues may make cooling savings unlikely. Next slide. And finally, let's look at domestic hot water heating performance from Site 3. After the scatter plots that we've just seen, it's maybe a welcome change that these are nice, clean profiles that we can look at. On the left, we have a chart for the average fraction of domestic hot water load supplied by the heat pump plotted versus outside air temperature. On the right, we have average daily domestic hot water heating COP for the overall system in navy, and for the heat pump alone in teal, also plotted against daily average OAT. Note that for this particular site, it had about 2 times the average domestic hot water load compared to the average single-family home in Minnesota. Here, the domestic hot water COP accounts for only the periods of time where the system was actively heating the domestic hot water. It does not include standby losses or all losses from reverting back to cooling mode in the summer. Instead, it is more representative of the average COP for all DHW preheating cycles that occur in a day. The average daily DHW preheating cycle COP measured was 2.7, although higher COPs were measured in warm weather above 70 Fahrenheit, as you can see in the chart on the right. The left chart shows the fraction of domestic hot water heating provided by the air-to-water heat pump. Because of the unusually large domestic hot water load at this site, we can say that the average residential customer might expect an air-to-water heat pump size for space heating to be able to supply up to 100% of the whole domestic hot water load. That is for daily temperatures ranging from approximately 20 to 80 Fahrenheit. Beyond these temperatures, an auxiliary domestic hot water heater likely still remains necessary. Recall that this system only provides domestic hot water heating when it's not responding to space conditioning calls, so domestic hot water was always treated as a secondary priority. This explains the clear peak on the left-hand plot, as the ability for the system to provide water heating is the inverse of the combination of heating and cooling loads. So we get less water heating when it's really cold, and we also get less when it's really warm out. But for a good band in between, we can displace a sizable chunk of the domestic hot water load at this home with an abnormally large need for water heating, so it's sort of a special case. Next slide. So now we've seen how these systems perform during our study, and knowing that, we can report how these affected the residents' energy needs, and maybe just as importantly, how they affected their pockets. So let's talk energy savings, costs, and payback from these systems, starting with this next slide. Here we have heating energy usage in kilowatt hours from all 4 sites when comparing the air-to-water heat pump to the baseline system. Recall that the seasonal COP was 1.35 for the NOAIR split system at sites 1 and 2, and up to 2 for the Enertech monoblock at sites 3 and 4. So the higher spec for these monoblock systems do yield higher performance in this case. Overall, we feel like this is quite a good outcome, where the energy savings are between 27% and 50%, or between 16 and 25,000 kilowatt hours per year. A notable takeaway here is that this is in line with our expectations for cold climate air source heat pumps in Minnesota, which we'll loosely define as inverter-driven products that are capable of operating well below freezing. Next slide. And here are the energy savings associated with domestic hot water only. And while this looks good as well, there are a few caveats here. As we mentioned earlier, the system at Site 3 only provided DHW when it was not responding to a space conditioning call, so domestic hot water preheating was not prioritized. This home also had an abnormally large need for water heating, about double the typical single-family home in our state. Still, the air-to-water heat pump displaced just under 30% of the load and produced an annual energy savings of about 40%, or 4,100 kilowatt hours. While the large absolute savings are attributable to the high load, it is likely that percentage savings will be larger at sites with more moderate hot water consumption. Next slide. Here are the estimates for cost and payback. The heating-only NOAIR systems were the cheaper of the two systems to install, with total upfront costs of about $15,000 and $19,000. Compared to the baseline electric boiler replacement of about $6,000, these installations will have a payback period of about 22 and 20 years. The Enertech air-to-water heat pump systems that meet heating, cooling, and domestic hot water loads have both upfront capital costs and labor costs being significantly higher. The incremental costs you see here are with reference to both a boiler and air conditioner outside unit. The larger savings at Site 3 are due to the space heating savings, plus an additional $289 per year from the displaced hot water load. While payback periods are close to or exceeding equipment lifetimes for these sites, it can be expected that incremental costs will decrease as the product class matures, more products become available, and installers gain familiarity with these systems. We also expect overall system performance to improve over time as products continue to be developed and optimized, lowering operating costs as well. We've seen significant performance gains from early air-to-air air source heat pumps compared to modern products, and there's no reason not to expect them with air-to-water systems as well. Next slide. And finally, let's talk about conclusions, barriers, and opportunities. Next slide. So just to reiterate, air-to-water heat pumps are air source heat pumps, but they just differ in their distribution medium. While relatively new to American markets, there are well-established solutions for hydronically heated homes internationally. Dozens of models and configurations are currently available, and they can fit virtually any residential application in Minnesota homes. The systems we observed brought space heating energy savings of 6,300 to 17,300 kilowatt hours per year, or about 27% to 50% in predicted heating energy savings in similar applications. The site with domestic hot water heating supplied by the heat pump saw 30% of their DHW needs supplied by the high-efficiency heat pump, yielding energy savings of about 40% that will likely be higher in the average home. Bill savings range from $450 to $1,400 per year, or between 27% and 53%. And while the payback period is at or beyond equipment life, upfront costs are only expected to decrease as this product segment matures. Similarly, we could expect further improvements in system design, construction, and controls optimization to potentially yield greater operating savings through performance gains, as we've seen with traditional air-to-air heat pump systems. Next slide. Now let's go over some barriers and opportunities. As we mentioned at the top of the presentation, high-temperature emitters like cast-iron radiators and older baseboard units may struggle to supply sufficient heating capacity, especially in cold winter. More detailed load and design calculations are required in such retrofit scenarios to ensure that the air-to-water heat pump will still be able to provide the necessary heating load with lower supply temperatures. As air-to-water heat pumps are a new technology to this market, barriers like limited workforce experience and a lack of standard rating methodologies will still hinder adoption. Although they are like other air source heat pump systems, the flexibility of air-to-water systems to work in many system configurations poses additional complexity and often requires more design work than boilers or even air-to-air alternatives. Air-to-water heat pumps have current opportunities in retrofit or new construction homes that feature low-temperature emitters such as radiant slabs or panel emitters. And additional opportunities for applications will still develop alongside familiarity with the technology. Next slide. And here are some recommendations from our project team. Air-to-water heat pumps carry benefits that are similar to or surpass other types of ASHPs, and they should be treated just like other ASHPs because they are by definition a subcategory of air source heat pump technology. We should therefore align with existing eco models and programs, and existing strategies for overcoming ASHP market barriers should be replicated for air-to-water systems. Stakeholders should also advocate for standardized ratings for air-to-water systems and can use established qualified product listings to make air-to-water systems compatible with existing air source heat pump programs. This type of strategy is employed by Efficiency Vermont with their QPL and is also adopted by MassSave and Otter Tail Power as well. And air-to-water heat pumps should also be promoted as potential customer solutions in any instance where a cold climate ASHP is determined to be beneficial but impractical to implement because of existing hydronic infrastructure. Next slide. The primary achievement of this work was capturing a snapshot of the state of the air-to-water heat pump market in Minnesota and demonstrating that they're available today and can deliver annual energy savings for both space conditioning and hot water heating in retrofit scenarios. But further work is still required to realize the full potential of the technology in Minnesota. And much of this work is related to market development, like workforce development, program development, and standardization. As we mentioned earlier, similar strategies that were employed for ASHPs can and should be applied to air-to-water systems as well. And while QPLs are a current solution, advocating for ratings and standards will help with program and incentive design moving forward, and they will also help customers and other stakeholders compare air-to-water options on level ground with competing system types that currently publish widely used ratings. Some research work also remains, and this includes clarifying the performance of these systems with different emitter types that are not included in the study. Controls optimization is another key area for future research, as this was something that we grappled with through the duration of the study. Optimizing controls out of the box can go a very long way towards increasing seasonal performance from these systems. Another key topic would be improving cooling performance, where there is a balance to be struck between making heating season adjustments that might sacrifice cooling efficiency, and also the effect of switching between cooling and heating for domestic hot water supply. While it was not possible with these systems, potentially dumping extracted heat from cooling mode into the DHW tank could improve how these two modes interact with each other. While these systems are capable of doing a great many things with a lot of flexibility, this does come at the expense of system simplicity. Complex systems are more expensive, they're harder to install and optimize, and could be more prone to failure while also being harder to troubleshoot. The integration of thermal energy storage with air-to-water systems is another promising direction for future research, where advanced storage options or even simple buffer tanks could yield extended performance gains. And finally, retrofits with high-temperature hydronic systems. This would include high-temperature emitters like high-mass radiators that may see inadequate heat delivery when used with lower supply temperature systems. Further research into retrofitting these systems to homes with existing high-temperature distribution will help us understand these limitations and the necessary additional design work required to remedy this issue. For our team, one thing we will be focused on is continuing our monitoring work on the monoblock at Site 3 through this heating season. Some balance of system adjustments were made earlier this spring, and we'd like to understand the effects of those adjustments through a complete season of heating. While these results will not be in the report, they will be published on the CE website once they are available, so stay tuned. Taking a longer view, monoblock air-to-water systems are increasingly marketed as a key technology for meeting tightening refrigerant regulations because they don't require charging on install and they don't have refrigerant lines within the building envelope. Reducing the risk of refrigerant leaks is also a bonus, as refrigerants can have a global warming potential that is thousands of times that of the equivalent mass of CO2. With the refrigerant safely pre-charged and tucked away in the outdoor unit, monoblocks are also candidates for low GWP refrigerants that can be hazardous and flammable. Perhaps one day they may even become the default type of air source heat pump, but who knows what the future holds. And with that, I thank you all very much for tuning in, and I think we will open for questions with this next slide of our $1 Million Smiles. Thank you.
Thanks so much for your great presentation today, Renal. Attendees, if you have not already done so, please type any additional questions into the Q&A panel and send them over to us. Lauren, are you seeing questions coming in? Do you have any questions for Samantha, Josh, or Renal?
Hi, Lindsay. Thanks for this. So we have over 20 questions that have been submitted. So I'm going to just pick some potentially as they come in and as we've kind of determined if they lead to larger discussion. So I'm going to go back to a question that Kevin Bright had, and then I'm going to jump to a question that Brady had. So Kevin's question was, were any of the examples conducted in an older home with radiators only? I'm assuming the homes are a bit newer as they have in-floor radiant heat. Josh, you answered that question. I'm hoping you can expand on that. But before we jump into your work, I'm wanting to also share Brady's question. And Brady asked, to Kevin Bright's question, for homes or multifamily buildings heated by boilers, radiators, would air-to-water heat pumps be the recommended path to electrification? Or at this time, would the recommendation be to retrofit the building to air source heat pump?
All right, I'll hop in here to reiterate my answer. This is Josh. These are terrific questions, and unfortunately, they're the key questions we have remaining with air-to-water heat pumps. First of all, we were restricted at the time of the study to look at efficiency technology, so we were looking for electric resistance heated homes. And it turns out that there's not a lot of electric boilers that feed cast iron radiators and baseboard radiators. So that was challenge number one. Of the few sites that we did study, though, we did find that they had emitter capacity that was effectively designed for supply temperatures of 160 to 180 degrees. And if we were to reduce the supply temperatures to those emitters down to the 130 or 120 degrees of these air-to-water heat pumps, we would have been unable to supply significant capacity to those emitters. Overall, we expected that we would meet only about 40% of the space heating load, and that wasn't really that interesting for us because we wanted to investigate these systems as the primary heating system. So it remains an open question about how effective air-to-water systems will be with emitters that are designed for higher temperatures. I will say that I'm still quite optimistic about the potential, because one thing we should also recognize is most of these high temperature emitters were designed for buildings that were built a long time ago. So even if we expect a lot less emitter capacity from those systems at these low supply temperatures, those buildings are very likely to have had significant upgrades that will have reduced their building loads. Things like weatherization and new windows may reduce the load on these buildings enough such that we could actually get adequate capacity for the building's needs at those temperatures. Unfortunately, this is like a really complicated question that was sort of out of the scope of our study because we would have to look in depth at the building loads and whether or not we could meet them with the heat pump under various scenarios. But I do think this is probably the most important research question that remains for air-to-water heat pumps, and that extends as well to the multifamily space where we would have the similar kinds of issues if we're looking at supplying older emitters with lower supply temperature air-to-water systems.
And just to jump in, one thing I will clarify, and maybe you mentioned this, Josh, is that it's not really a question of whether, assuming they're properly sized, whether the heat pump will be able to produce the capacity, but rather whether that capacity can be effectively delivered to the home via the high temperature distribution system.
Yeah, that also reminds me of another thing. If you could go on here, we actually saw some of this already when we started promoting condensing boilers a long time ago. They also deliver, for their optimum efficiency, supply temperatures that are considerably lower than these design temperatures. And so it's this sort of constant battle between the emitter capacity you can get out of your existing emitters and what you need for your building. And the challenge is actually kind of a little bit separate from the heating plant, which can deliver sufficient capacity at those temperatures.
Awesome. Thank you, Josh. Thank you, Renal. I'm actually going to take the next question. Will Inflation Reduction Act rebates apply to these systems? Rosanna, that's a great question. The state, the federally funded state-run Inflation Reduction Act programs, those have yet to be defined. So at this point in time, that equipment has yet to be defined on a very specific level. There is information in Minnesota statute that this type of equipment will be, but the details of the programming is still being worked out. Lindsay, do you have any additional insight on IRA?
No, I do not.
Cool. So I'm going to kind of continue with these questions. So Ann Kraft asked, what is the expected life of the equipment?
Josh, would you like to take that?
Sure. I think where right now the life is consistent with other heat pump systems, which is between 15 and 20 years.
Awesome, thank you. And then we got a couple questions about sending the presentation after. This presentation will be shared. I think Lindsay gave a timeline at the beginning, but yes, this presentation will be shared. Continuing down, what are the flow temps for heating, cooling, and domestic hot water for each site? And it looks like, Sam, you answered that. I'm sorry. Talked about IRA. And then Charles, thank you for your questions on heating pools. You had a question on any suggestions on where I could look for information on air-to-water heat pump use in the swimming pool heating application. Apparently they are used in the application, especially for outdoor pools in warmer than Minnesota climates.
I can hop in and share some speculative thoughts. Renal and I, in a separate project, have actually looked at air-to-water systems for swimming pool heating, and I think Sam May noted conceptually they're very strong for this application because they have a relatively small temperature lift over a relatively narrow band of outside temperatures, and that would even be the case in Minnesota because presumably people won't be heating their pools once it gets too cold outside. I do think though that there's probably specialized equipment that's focused on that operating range that will be much better than sort of these all-purpose systems that we studied here. I know in the previous project that we were looking at some air-to-water systems for pool heatings that convincingly were claiming their COPs were 5 or 6 for heating pool water, which is extremely it has a lot of savings compared to conventional pool heaters, which are going to be at either combustion efficiencies or electric resistance efficiencies.
Thank you, Josh. We have a question from Michael Noble. Is the cooling function always done via an air handler and a coil?
I can jump in to answer that question. Good question, because the answer is it does not have to always be an air handler and a coil. For our study sites, they happened to all deploy cooling through an air handler and fan coil. There are some modern emitter types, similar to mini split heads that are essentially radiators that have little fan coils inside of them, that could be very promising for cooling applications too. The main reason that we don't or didn't use the slab for cooling is due to some remaining concerns about condensation on the floor, which could be hazardous for slipping and cause a bunch of problems due to water damage. So that's the primary deciding factor on what kind of emitter is suitable for cooling, is whether or not you'll be able to provide sufficient cooling without risk of condensation. It's possible potentially that floor emitters could someday be designed so that humidity is managed in a different way to eliminate that risk. However, there's not a lot of data out there yet to support that strategy.
Thank you, Sam. Jumping to our next question. Pat asked if current in-slab hydronic system is working well, being supplied by high efficient propane domestic hot water heater and a flat plate heat exchanger. Could domestic hot water heat pump replace propane hot water heater, or could that possibly work? Or is a split type system likely needed?
I'll distribute that one to Josh also.
And we can also take some of these questions offline and provide a response after this presentation if we don't want to answer that verbally.
I think I would like to take some more time to answer that one carefully.
Awesome. I'll take note of that. And Pat, we'll get back to you. Josh has a question. Are you also addressing the marketing of air to water with storage? Many older folks have seen heat pump technology before and think it's not possible for Minnesota. It is, but we need to update folks.
Question, Josh. So in this study so far, we did not really study how these systems can be integrated with storage. You could technically view the domestic hot water preheater as a version of storage. It's essentially a hot water tank that the system keeps warm all of the time. And so that is sort of a form of storage. And these systems seem really well poised to be matched with storage because water tanks are a very low cost way to store heat. There are also exciting new storage technologies out there that can store more energy in smaller space, using new phase change materials. And so this is something that really we would love to study in the future, and see how much further storage aspect could bring the performance of these air to water heat pump systems by temporarily allowing the system to maintain capacity even in cold temperatures from the storage, or by just improving efficiency by optimizing the supply temperatures and the time of day that the heat pump is running. So that's a great question. And unfortunately, we don't have the answers yet. And they definitely are something that are on our radar to be looking at.
Awesome. Thanks, Sam. We only have a little bit of time before I have to hand it back over to Lindsay. And I'm wondering, you three, was there a question that you answered previously that you want to touch on as a larger group? If not, I have one question I would like to answer or have answered. And then I want to let everybody know that we did receive a lot of questions. We will go through these and we will provide responses to you, written responses to you. So Sam, Ronald, Josh, are there questions that you answered previously via text that you want to expand upon now?
That on my side, Lauren.
Awesome, thank you. So I am going to ask my question. I'm sorry to kind of take over this, but you all discussed air-to-air air source heat pumps and air-to-water heat pumps. When would a homeowner or contractor consider one retrofit application over the other? And then what about a residential new construction application?
Great question, Lauren. So I guess I want to reiterate that air-to-water heat pumps are air source heat pumps. So we expect similar performance between the two different technology types. And so the main factor in determining what sort of system is the best fit for any application really lies on what kind of distribution system is planned and is the best fit for the building. So if the building already has hydronic distribution, air-to-water heat pumps are great to consider. And if the building does not have hydronic distribution, it's likely far more cost effective to use an air-to-air heat pump instead of an air-to-water heat pump. And in new construction applications specifically, air-to-water heat pumps might be particularly interesting because that provides the designers the opportunity to take all these things we've learned about how important the emitters are in their configuration and ensuring that you can meet the load of the home and design that specifically for an air-to-water heat pump from the start, so that these, like I mentioned, these fan coils that could be used for heating and cooling simultaneously without a central air handler, those could potentially be considered in new construction, and that will be a lower barrier compared to a retrofit application since you're not having to displace already existing infrastructure in a new build.
Appreciate this, Sam. So I'm actually going to send it over to Lindsay, but I appreciate everybody's questions and responses today.
Excellent. Thanks so much for facilitating the Q&A, Lauren, and to Samantha, Renal, and Josh for your thoughtful responses. Attendees, if you have any follow-up questions, like Lauren said, we'll work on getting questions answered in a written format and sent out when the PowerPoint is sent out in a couple of weeks. But also, Samantha, Renal's, and Josh's contact information is here. So, please feel free to reach out directly to them too. As I said, the slide set will be emailed to all webinar registrants within a couple of weeks with the answers to the remaining questions. The recording of this webinar and slide set will be available on the department's website along with the final report, typically within a month. When available, you can link to either of these from our quick links on our Applied Research and Development webpage indicated on this slide. The department's R&D webpage has additional resources and information related to the CARD program and to CARD research projects, which you can check out by going to the website address noted on this slide. The department's website recently underwent a major change and is continuing to undergo improvements. This webpage will look somewhat different soon, so please do not hesitate to contact me if you have any questions or concerns related to accessing CARD research. So again, thanks so much to attendees for participating today. We appreciate your interest in CARD projects. I want to take a moment to mention an upcoming CARD webinar on February 20th. LHB and Slipstream will present on results of a commercial field study of phase change materials for passive thermal regulation. And to keep aware of upcoming CARD webinars as they are scheduled and other news related to Minnesota's Energy Conservation and Optimization Program, don't hesitate to sign up for the SIP updates through this, through your email, through our email list. You can use the link on this slide to do that. Or if you, I could also email that opportunity to sign up for the newsletter as well if you would reach out my way. In the meantime, contact me if you have suggestions or questions related to CARD or CARD program webinars. So there'll be a short evaluation that launches after this webinar. Please take a few minutes to fill it out and let us know how we did. And with that, thanks again to everybody, the presenters, the attendees. This ends the webinar. Take care and have a great day.